Good evening, everyone. My name is Jay Parsons with the University of Nebraska-Lincoln, and it is my pleasure to welcome you to this evening's webinar titled A Journey, the Opportunities and Challenges of Melding Genomics into the U.S. Sheep Breeding Programs. This webinar is brought to you by the Let's Grow Committee of the American Sheep Industry Association. We'd like to thank them for their support and encourage you to visit their website to learn more about the American sheep industry and to access the large volume of services and resources available from ASI to help you be successful in the sheep business. The URL for the ASI website is www.sheepusa.org. You can access the Let's Grow materials by clicking the Rebuild link under Programs on the main menu. You can also access the Let's Grow materials directly by using the URL www.growourflock.org. Before we begin, I'd like to remind our listeners that this webinar is being recorded. All webinar registrants will receive a follow-up email within the next 48 hours with a direct link to the webinar recording, as well as a link to access the webinar slides. Links to these materials, as well as all the recordings and slides from our past webinars, are also posted on the Let's Grow website. We're slated for about a 45-minute presentation that'll be followed by about 20 minutes of questions. Feel free to submit your questions at any time during the talk by using the question box in the lower right-hand side of your control panel. You can just type your questions right into that box and I'll see them on my end and be monitoring those and moderating them to our speaker during the Q&A session. Also during the Q&A session, if you want to talk directly to the speaker and ask your question, because it's rather complicated or might have several parts to it, you can do so by raising your hand, and I'll go over that procedure when we start the Q&A session itself. So with that, it's my pleasure to introduce this evening's speaker, Dr. Ron Lewis. Dr. Lewis is a professor of animal science at the University of Nebraska-Lincoln, specializing in animal breeding and genomics. He earned a bachelor's degree in animal science from the University of California, Davis, and a master's degree in animal breeding from Texas A&M, before going on to earn his PhD in animal science from Virginia Tech University. His work experience includes a 2-year stint in Western Australia as a geneticist and 9 years as an animal breeding specialist and the leader of the sheep breeding section of Scottish Agricultural College in Edinburgh, Scotland. In 2001, he returned to Virginia Tech University as a faculty member in animal genetics, and he stayed there until 2014, when we were lucky enough to hire him away to come here to the University of Nebraska-Lincoln. As you can see, Dr. Lewis has focused on the topic of genetics throughout his career, but he's been pretty diverse in terms of the locations around the globe where he's worked on this. So that brings its own unique experiences in and of itself. And I know one of his current experiences is that he has a Let's Grow project with ASI where he's exploring this topic. And I know he's going to touch on that a bit in his talk. So with that, it's my pleasure to turn things over to Dr. Ron Lewis to begin our journey of addressing the opportunities and challenges of melding genomics into the U.S. sheep breeding program. So Dr. Lewis, the floor is yours.
Well, thank you, Dr. Parsons. I appreciate the invitation and the opportunity to speak about this topic. I'm not sure I recognize the fellow who you just introduced, but I'll do my best to tell a little bit about my journey over these past years. That relates very much to the topic of the evening. For those of you who I've not had the pleasure to meet, I'll let you know that I'm not far off 60. And that has a real context in how I look at this. My formal training was well before these ideas of genomics and molecular genetics were a twinkle in anybody's eye. And so I've come to this idea of how we might use these tools from really a very traditional background in sheep breeding. And what I hope to do tonight as I talk through my views about opportunities and challenges that these tools provide is to give you a sense of my journey with the hope that it might help you keep these ideas in perspective and how we might be able to use them to help our U.S. sheep industry. So with that very brief introduction, let me outline my talk and the way I will take us on what I call this genomics road trip. What I first want to spend a little bit of time is talking about the terminology, if we don't have a sensible starting point in terms of the tools that molecular genetics have and the jargon that it entails, it's hard to put them, to ingrain them into what we do within our sheep breeding programs. So I'll spend a little bit of time using a map as my framework to talk a little bit about the tools of genomics. And then I want to reflect on what those tools mean to us, or what they may mean to us, as we think about integrating them into our sheep breeding programs. And there's an idea called the key equation, or the breeder's equation, that I'll spend a little bit of time on to put in perspective the way I believe we can bring in these tools to use them very effectively in our sheep breeding programs. I'll then go on and talk a little bit about the bumps along the road. Any technology has some hiccups as we try to think about how to incorporate them into what we do. And so I want to focus on two of those that I think will face us in the sheep industry, so we're realistic, if I may, about where I think we're going to need to go to if we really want to incorporate genomics into sheep breeding programs. And then I briefly want to finish up about starting a new trip. And what I mean by that is there's a lot of use of these tools in other livestock species, use internationally, and I think there's real opportunity for us to collectively move forward in thinking about how we wish to use them in the U.S. And that I'll give a bit of an overview as I start, provide some ideas about starting a new trip. So that's the context of my talk this evening. So let me start with a map. I hinted that I want to use the map as my structure of talking about these tools. And this clearly is not a genomic map at the moment. It's a city map. And I think it provides a good sense of what we're really trying to do with our genomic tools. What we're trying to do is to define a better map. And I think we can see that by first thinking about a standard geographic map that we might use. My dear wife Esty and I, about a couple of years ago, took the decision to make the move from Virginia to the University of Nebraska-Lincoln, and that involved packing up and taking a road trip to bring us here. And so we had to figure out how to get to Lincoln, Nebraska, which I'm showing as a circle here. So we traveled through several states, continued up through Missouri, hit Nebraska City, took Highway 2, and we ended up to settle in. And then, as all of typically must do, I had to think about how to get. So I needed a map that told me more than where Lincoln was within the United States. So I needed a map that would direct me to where my office was on the University of Nebraska-Lincoln campuses. And in order to do that, I needed a map that was more detailed than this grand road map of the United States. And so I got a hold of a map that looked something like this. It turns out that UNL has two campuses. There's the city campus, and there is the East or agricultural campus. And it turned out that my office sits at the East campus. So now I have a little bit more information about where I was going to end up needing to go as I began my position. But it still isn't quite specific enough. I actually ended up needing to figure out where the animal science complex was in the East campus. So in order to do that, I needed an even more detailed map, a map that was denser, provided me with more information. So I got a hold of a map that looked something like this, with the area outlined in yellow being the animal science complex. And so I could find my way to my building. But there's an important component to this. I've still not yet found my office. What I have found was where the animal science complex was. I was a lot closer than I was before when we left Virginia to getting to my office, but I had not yet gotten there. In a way, that's where we are with these genomic sciences. We have maps that are becoming better and better and better, but we're not yet at the point where we're identifying these individual genes, if I may, that are going to tell us about the underlying mechanisms that control the way animals perform. So we need to be realistic about where we are and how we can use a detailed map, but not an explicit map, to help us as we take decisions in our sheep breeding programs. So let me give you an example of what a chromosomal roadmap looks like. It also kind of like a geographic map. It's got kind of the main highway, and along it are signposts, which in this case are individual genes. So those genes provide information about where we are along a chromosome. But in reality, we don't know where all the genes are. And only with a more detailed map are we actually going to ultimately get a sense of what these individual genes do. And so at the moment we have this roadmap, we have some road markers, but it will be a bit of time before we actually get the additional detail, if I may, in order to explicitly see every location along these chromosomes. That is, find my particular office. So this is the tool that we currently have, and it's a very informative tool. And what we now need to do is, using this dense but not complete map, is we need to think about how our road signs, how the genes that we have identified link to the way animals perform. Now I'm going to reiterate this again and again through this talk, and I apologize if it begins to feel redundant. These genomic technologies will not, again, they will not replace what we do in our traditional breeding programs. We will need to continue to collect performance information on our animals, because we need to be able to link these genes, these signposts, to things that animals actually do. And we can only do that by collecting performance information. There's a view that, in fact, there's some terminology that people say that in this genomic revolution, phenotyping will actually become king. That is, phenotyping even becomes more important. So we need to understand that the genomic tools will complement some very good techniques that we currently have. We'll be able to do a better job, but I doubt that we're going to see them replace the current approaches that we currently use. So with that said, let me provide a little bit more about the terminology so we can move towards thinking about how these genes are going to help us, how genomic tools are going to help us in our sheep breeding programs. There's an idea called major genes, and it turns out that for some traits that are economically important to us, we have indeed found that golden location along the map. We have found genes that we know have very major impacts on things that are important to us. And here are some examples of that. We have some genes that we know affect fecundity, mastitis susceptibility, muscling like the myostatin gene, the ovine pneumonia, progressive pneumonia virus resistance, scrapie resistance, spider syndrome. We have successfully found genes that tell us whether or not an animal carries an advantage, a benefit for some of these particular conditions. So we have found some of those major genes. But in reality, these major genes are comparatively rare. They aren't the norm. Instead, it turns out that many of our traits that are of interest are actually much more complex than we would have anticipated 20 or 30 years ago when these tools were beginning to come into the forefront. In most cases, traits are instead influenced by thousands and thousands of genes, and each of those genes have a small effect. So no one gene has an overwhelming impact on the way animals perform. So when we recognized that these major genes weren't the norm, they were the exception, we had to think a little bit about what do we do with the fact that we are really still working with thousands of genes, each having a limited impact. So So there's a very fundamental paper back in 2001. I won't say much more about it, but what it flagged is we needed a broader approach. We couldn't hunt for major genes to solve all of our problems in our agricultural systems. And so this is what that broader approach led us to understand. What we're able to do is to identify some genes. Those are the genes that I showed along that chromosomal roadmap. And it turns out that some of those genes, our roadmap genes, in this example, I'm showing my A gene, may be nearby something that is causative. It does affect a trait that we're interested in. And so, for example, we might have a circumstance where A provides an indication, a marker for something that has a causative effect, in this case, capital A being associated with little j on our chromosome, which turns out to be important. It has a causative effect. And so maybe this gives us a little bit more growth rate or a better eating quality or a slightly finer fiber. So J provides that benefit, but we haven't found J. Instead, what we really found was A. And A then serves as a marker that an animal also has that little j. But coincidentally, maybe that little b also has a causative effect on one of the traits that I just mentioned. So if an animal had a little j and a little b, it means that it may have a slight advantage in terms of growth rate or fleece quality or some other trait of interest. So A is our marker, J is the gene that's actually having the causative effect. Now notice B is a lot farther away from A than J is, and that becomes really important when we think about the way we apply these tools. When the locations of our marker, in this case our capital A, is physically closer to our causative gene, for example our little j, it provides a much more consistent link between our causative gene, our little j, and our marker A. Given the greater distance from capital A to little b, that relationship is less persistent. And so the whole bottom line of this technique is if A always sticks with little j, if I select an animal that has the capital A, little j rides along with it. It is less likely because of longer physical distance between capital A and little b, that B will ride along with capital A when I select an animal based on that capital A allele that we've actually found. So that's the bottom line of how this technique actually works. And so it turns out in sheep we have this what we call a bead chip, the Illumina ovine SNP 50, and it has about a bit over 50,000 road marks along the chromosomal map that we have in sheep. And there are a number of chromosomes in the sheep genome. So we have 55,000, somewhere in that ballpark, road maps. And what our hope is that some of those markers align fairly closely with genes that are causative. So if we select an animal that has a particular gene at our roadmap, at our marker, we also carry along with it the causative gene that allows us to impact the way animals perform. So that's the bottom line of the technology. And where that becomes important is when we're trying to figure out, is one animal genetically better than another? I've already hinted at that we're finding that these individual causative genes tend to only explain a small amount of the variability. And so what we really want to do is to identify those animals that have many more of these positive causative genes, because along with that will come improvements in their performance. And so what we do is we try to gather up, to collect all that information in calculating what we call genome-enhanced breeding values. And these sounds like a fairly fancy, complicated name, but it's really a fairly straightforward idea. we have these 55,000 roadmaps. We're hoping they're associated with causative genes that affect a trait of interest. And what we do is we just kind of sum them up. So we sum up those that are having a positive effect. We account for those that may not be having a positive effect. And we use that accumulated information to try to do a better job of really delineate this animal is genetically better than an alternative animal. That is what we call the genome-enhanced breeding value. We're incorporating the genomic information in our evaluation to try to identify animals that are better in their genetic merit. And by doing that, by using all of that additional information, we're able to more accurately figure out which animal or animals are actually genetically better than others. So that's the bottom line. Now again, stepping back to this idea, that doesn't get us away from needing to have performance data. The predictions that we use, the link between our 55,000 locations along our chromosomal map, still needs to be linked to performance trace of interest. So we have to tie this map to things that we measure in animals so that we can actually figure out which genes impact the way this animal actually performs. So that will remain the bottom line of the technology. And if we do this well, these are some of the improvements in how accurate, how reliable we're able to predict an animal's true genetic merit for some traits of interest. So, for example, from some work in Australia on carcass and meat quality, we can get improvements of 5 to 10% in how accurate we're evaluating our animals. For traits like meat, fleece, and litter size, some work out of New Zealand, the benefits are between 5 and 27%. For milk production, 10 to 20%. So we're getting real differences. We're able to do a better job of figuring out which animals are genetically superior than others. Now, the extent of that gain in accuracy is related to how much we know. So the more genomic information we have, the more performance information we have, the better we are in able to improve the accuracy of our selection decisions because we do a better job in figuring out which animals are actually truly genetically better. Okay. So that was a little bit of a journey, if I may, through some of the technology to give you a little bit more background in what these tools actually are. Okay. So now what I want to do is to put it into perspective in terms of how we meld these ideas into what we do in our traditional breeding programs. And to do that, I need to refer to something called the key equation, and then I'll give a couple of examples of how I think genomics will help us to build upon that key equation to do a better job in our breeding programs. So this is a key equation. And I know most of you sitting out there going, what is this horrific looking thing that this fellow is putting forward to you? And let me put this in perspective. When I've shown this key equation to my dear wife, who happens to be a musicologist, she looks at it this way. She sees it as truly abstract art. And at times, I'm certain when I present the same equation to my undergraduate students in animal breeding and genetics, they see it as being simply chaos theory. Well, me, being what I do and my love, I take a slightly different perspective because I see that equation as true poetry. And what I'm hoping I'll be able to do is to show you how this poetic equation helps us think about how genomics can help us in our breeding programs. So let me break this equation down. It's not quite as terrible as it might look. The bit here over on the left-hand side really is all about how much genetic gain do I make per unit of time. So how rapid am I making genetic progress? If we stay on the top of the equation, this first value is what we call the accuracy, And as we would anticipate, the more accurate we are in our ability to delineate genetic differences, the more gain we're able to make in our selection programs. This I with this subscript X, that's how intensive we are in our selection. Clearly, if we're selecting fewer animals, if we're being more picky in those that we keep in our breeding program, we're able to make quicker rates of genetic gain. And the last term over here on the right-hand side has to do with how much variation we have genetically for the trait. Traits that have more genetic variability have greater opportunity to make genetic change than those that are less variable because we have more variation to work with. So effectively, we want everything up here on the top to be big, because if it's big, it means we're going to be able to increase how quick our response to selection is in our breeding program. On the bottom of the equation is this thing called L, which stands for the generation interval. And that has to do with how quickly we turn over our generations. If we turn our generations over more quickly, it means we're bringing in new, hopefully higher merit animals into our program. And so if we can keep L small, it tends to help us increase, because L is on the bottom, it helps us increase the rate of gain. So the goal of the design of any animal breeding program is to try to keep everything on the top big, the L on the bottom small, because when you work out the ratio, you make more gain. Sadly, and in reality, it's not quite so easy. Typically, L and at least several particular accuracy move in the same direction. So typically, when we increase accuracy, it drags along with it an increase in L, an increase in our generation interval. And this is one of the beauties of what genomics allows. It provides us a way to break up that relationship. So we can actually improve accuracy, yet at the same time, actually reduce the generation interval. So let me put that into words. This is what the genomic tools can allow us to do. We can be more accurate in identifying animals of higher genetic merit because we are able to create these genome-enhanced breeding values, which do a better job of figuring out which animal is of higher true genetic value. At the same time, we are able to actually decrease the generation interval, and thereby higher accuracy, shorter generation interval, we're able to make more rapid gain. So that's the bottom line. That's really all we're trying to do with these genomic tools. We're trying to make more gain by manipulating the component of this key equation. So let me give you a couple of examples of how that actually works in practice. I think for most of us, we find at times trying to figure out the pedigree of an animal can be a little bit tough. And it particularly becomes hard when we have breeding programs that use multiple sires and when our production systems are in extensive environments. It can be very hard to pair up a lamb to a ewe and therefore to its sire. Well, one of the things that genomic tools will allow us to do by the use of what we call parentage panels is that with a limited number of markers, by having a bit of blood on the sire, a bit of blood on the lamb, perhaps even a little blood on the ewe, we're able to determine parentage without actually pairing up lambs with their dam and thereby their sire. And by having these more accurate pedigrees, we're then able to increase the accuracy because we're able to figure out that the true sire and dam of a lamb is a particular pair of animals. So by knowing that pedigree relationship, we're able to figure out which lambs relate to which parents, and if we identify better parents, we're able to link that to better lambs, and as a consequence, we can do a better job of identifying those of higher merit. So we can build a better pedigree by using these parental panels, one of the advantages of these tools. The other one is to improve what I call difficult to measure traits. In my heart, I think these tools are not going to be most useful for us to evaluate things we're already pretty good at. Body weight, fleece weight, some characteristics that we're pretty good at being able to measure and make good gain with our current traditional tools. Where they're going to be really valuable is when we start considering traits that are more challenging to measure, things that we can't really record until an animal's late lifetime, things like their longevity. Traits that are expressed in only one sex, fertility, litter size, mastitis, things that we only record in females. Traits that are either expensive and or challenging to measure, lamb survival, maternal bonding, aseasonality, carcass and eating quality traits, the efficiency or feed efficiency of our livestock in our seed stock and commercial operations, and perhaps even things in the future like methane emissions, as there are concerns and pressures on environmental variables in our farming and ranching systems. So if we have ways to use genomic tools to get a hold of these more challenging traits, we then can implement ways to make improvement. And so focusing on these difficult to measure traits, I think they give us two advantages in terms of that key equation. We're able to increase the accuracy because we'll have more information through these genome-enhanced breeding values, and because we can then measure some of these things at a younger age. We don't need to wait until a ewe is at the end of her lifetime to identify whether we think she has genes that give her greater longevity. We can start evaluating these at very early ages. And that's truly been the case in the dairy cattle programs. At the moment in dairy cattle, there are programs where they're actually identifying bulls to keep as replacements when they're still in utero in the cow. So the generation interval is actually becoming before birth. It's very optimistic. I don't see that being able to come into play in the sheep industry, but it gives you a sense of the opportunities that we indeed may have. So there's some real positives. I think there are ways we can use genomics to help us make better gains in our sheep breeding programs. But there are bumps along the road. There is always considerations when we think about these technologies that we need to be sincere about and to think about. So let me talk about two of those that I think are pretty key, what I call reference populations and simply the costs of genomics. I already hinted at that the accuracies of these genome-enhanced breeding values really depends on us having lots of genomic and performance information. And to do that, we are required to have what we call large reference populations. And these are no more than populations that we do a lot of performance recording in and we collect a lot of genomic information on. And these populations need to be big in order to capture all of that genetic diversity you enjoy within your individual flocks. And it turns out that we really release information, these large populations, on individual breeds. Everything that we understand about these tools to date says they don't translate well across different breeds. And so it means we need large populations, not for all sheep, but we actually need large populations that are specific to individual breeds. And as you well know, we have lots of breeds of sheep that are here in the United States as well as across the globe. And it turns out that we can't look at the relationships between performance and genomics only once, but we need to continue validating the links between our genes and the way animals perform. As the information that we have on genomics becomes ancestrally more distant, our predictions become poorer. So we need to continually update these links between our roadmap and the way animals actually perform. And let me put that quickly into perspective with this diagram. Along the vertical axis, we have the accuracy of genomic prediction. On the horizontal, it's the size of our reference population. And the different lines reflect two things: a case when we have what is called a smaller population size, and these are populations that are probably going to be more consistent with some of our terminal sire breeds, or larger population sizes, which are going to be our range sheep, our wool breeds. And so we have two different heritabilities. The solid lines are traits that have relatively high heritabilities. The dashed lines are relatively low in their heritability. And with lower heritability, they're inherently harder to change by genetics. Now, if we think about the sizes of our populations in our programs, the calculations would say that in some of the populations that are comparatively smaller, I refer to the terminal sire breeds, we're going to need reference populations of 4,000 animals. And as we move to these range operations, to some of our wool breeds as an example, those populations are as large as 10,000. So it's a huge commitment of resources to develop these reference populations. And I hinted at a moment ago that we also need to keep things up to date. So if we establish a reference population of 4,000 animals, about 12.5% of that number need to be evaluated year in and year out. So after we do our initial screening, developing that population for a reference population of 4,000, we need to collect information on about 500 additional animals each and every year. For a population of 10,000, we're talking about an additional 1,250. And so there is going to be this ongoing need, this commitment to continue to collect genomic as well as phenotypic information. And it is costly. We need to be realistic. The value of an individual sheep is comparatively low, but at least at the moment, the cost of genotyping is nearly the same across species. So for collecting that genotypic information, it would cost me about the same in a sheep as it may be in a dairy cow. We're hoping those costs will fall, but I think in the meantime, we need to be a little bit strategic in how we think about using these tools. And there's some ideas on how we might do that effectively. What we may wish to do is to use that 55,000, that higher dense chip, to collect information on the genome, on key rams, key sires in our breeding programs. And then to use a lower density chip, something that may have 2,000, 5,000 markers along that roadmap in many of our other sheep. And it turns out that if we have that very high dense information, we're actually able to fill in some of the blanks in our roadmap on those animals that we have low dense or low density information on, and we call that imputation. So we can gain information linking the high to the lower density genotypes. And the animals that we're going to probably want to collect this low density genotype on will be young animals. And I think there's some opportunities to think about using mature ewes that have lifelong genotypic or lifetime, performance data, particularly when we want to start looking at reproductive attributes, maternal characteristics, and the like. And I see there's some opportunity to collecting very limited amounts of information that allow us to do parentage and to hold on to some of those major genes that I introduced earlier on. So I think there's ways that we can collectively be a bit more cost effective. So that's the journey. And what I want to now move on to is how this all comes together, how we might imagine how we can use what we know, some of the constraints, challenges we're going to have in applying this to our sheep industry in order to move together collectively. And that involves who we genotype. By that, I'm saying who we actually visit and how we need to think about this as a collective effort. So let me offer a few comments in that idea. I very kindly was awarded through the Let's Grow program some funding for a project that has a rather long name, Engaging the New biology, establishing the foundation for genome-enhanced breeding values in the U.S. sheep industry. And Dr. Parsons made mention of this during the introduction. And with that funding, there are a couple of opportunities that I hope to be able to share with you. One of the objectives is to provide education on genomic tools, and I'm hoping in the webinar tonight I'm moving us a bit in that direction. Another important part is to think about how we might go about collectively collecting this genomic data. How do we start the journey together? And I have several ideas on how we can end up doing that. One of them is to think about how we most effectively sample animals, and won't go into much detail here, but I and some colleagues have 4 different ideas in mind, and one of them is trying to take into account genetically how closely related individuals are. Oftentimes we can learn more by finding animals that are less genetically related, because they give us a greater view of all of the genetic diversity out there in your flocks. And we have some methods to go about identifying those animals that might provide us that little bit more information as we're trying to collect genotypes. So the program will allow us to think through and start to apply some of those sampling strategies. And at least as the starting point, we're going to do that as follows. We're going to use something called blood cards that allows us to collect a high quality genomic sample. And we're going to do that on 1,000 Suffolk and 1,000 Rambouillet sheep that are part of NSIP. And I'll reemphasize, having that performance data is key. If I have genomic data, but I don't have performance data, I can't seed my roadmap into something real about the way these animals perform. So it's essential to integrate the genomics with the performance recording. And so we are recruiting flocks and sheep using some of our sampling strategies in order to begin to collect this information. And what our outcome, or intended outcome is to begin to collect this reservoir of genomic samples that we're going to need in order to develop these reference populations. Only through those reference populations are we going to be able to tie our roadmap, our genomic roadmap, to performance. From that, we can calculate these enhanced genomic or genome-enhanced breeding values, and thereby be able to benefit yourselves as breeders in doing a more accurate job of identifying higher genetic merit animals. And to do this, we're going to need to share the road. I feel very, very strongly about this. I think if we're going to incorporate genomics into the U.S. sheep industry, we're going to have to collectively think about 2 things. It's going to require 2 key elements. We're going to have to do extensive performance recording. That's going to be continue to remain to be very important. And we're going to have to be strategic about our genotyping in order to deal with the cost and to develop these most effective reference populations. And we're going to have to be realistic about the cost, and we're going to need to think about how we handle that collectively as an industry as we move forward. It's going to cost dollars, and as importantly, it's going to take all of our time and enthusiasm in order to continue this journey towards incorporating sheep genomics into our breeding program. And so I strongly believe this can only be achieved together. This is not something that a scientific community will be able to do on its own. It's not something industry is going to be able to do on its own. This can only come about if we collectively merge our enthusiasm and our wisdom in a way that we can effectively and profitably use sheep genomics as an add-on to our current breeding programs. And I certainly look forward to the opportunity to be able to work with you as we continue down this new journey as we go forward. And to finish up, I want to thank you for your time and listening to my presentation. I very much appreciate the invitation to present this webinar. I very thankful to Dr. Parsons for helping to organize tonight's event, and I'm very grateful to ASI and Let's Grow for their ongoing support, and I look forward to that interaction continue. And I'm hoping I've generated some questions, and so I will turn the floor back over to Dr. Parsons, and hopefully we can have a nice discussion as we continue with this webinar.
Thank you, Ron. That was fantastic. And you have generated some questions, surprise, surprise, right? So I'll get to those in a second. I just want to reiterate, if you have questions, you can either type them into the question box down in the lower right-hand side of your control panel. If you want to talk to Dr. Lewis directly because you have a multi-part question or maybe it's hard to type it out, feel free to raise your hand and I can unmute your microphone and you can talk to him directly. There should be up in the upper left side of your control panel, there's a little tab there with a hand, and it's on that hand that you click if you want to do that. So let's go ahead and we'll launch into our questions here. We had several of them come in while you were speaking, and I'll try to get to them in the order they were asked and more or less refer you back to some of your slides that you had there. If I'm off a little bit, the listeners feel free to type in and let me know that I was off a little bit in asking your question. But we had a question on inbreeding, and this is back when you were talking about improving and actually the difficulty in measuring traits with them. And the question was, how is that affected by the overall inbreeding in the population of interest?
So Jay, to make sure I understand, so the idea is, will genomics help us understand inbreeding better?
Well, is there an issue with the inbreeding in terms of measuring these traits that you're seeing or not seeing and your ability to measure them?
Right. Typically, inbreeding comes about, or it doesn't typically, inbreeding comes about by mating animals that are more closely related to one another. That's how we create inbred livestock. And when they're inbred, it means they also have more genes in common. That has an impact on how genetically diverse they are. But inherently, that doesn't impact our ability to measure performance on those individuals for these various traits. It may indeed have an impact. There's this idea called inbreeding depression, which can, and it's particularly prevalent for traits that affect things that we refer to as fitness, like longevity, reproductive rate, these sorts of characteristics that deal with how fit an animal is overall. Now, there is a risk with these genomic tools that we more accurately identify animals that are of higher merit. They then tend to come from the same families, and as I mentioned a moment ago, inbreeding comes about intermating related animals, so there is a risk that we can increase the rate of inbreeding if we don't use these tools carefully. That said, the genomic information tells us explicitly what is the genomic makeup of a pair of animals. And so we can actually quite intimately compare that genomic makeup to say how closely related are they genetically, and therefore have a better sense of how inbred they are. But inbreeding in its own right doesn't affect our ability to measure performance, but indeed, particularly for traits that impact fitness, it can cause some depression in the way animals perform. And so we need to consider that in the way we apply these tools as well as any other tool in our breeding programs.
So if I'm understanding correctly, in terms of the genomic science itself, you can see that they're highly inbred from the genetics that you see. Is that correct? And the follow-up to that was, if there's less variation, is genomics less useful, in the population itself?
It's an excellent question. Jade, going back to the first part of that, yes, using these genomic tools, we can do a better job of measuring inbreeding because we don't base it on probabilities, we base it on actual genomic similarities. And indeed, in any breeding program, if we get carried away and don't try to maintain genetic diversity, there is some risk that we lose some of the genetic diversity we have in our populations. But there are a number of strategies that we can use to try to balance these ideas. And it really boils down to having a long-term vision. What we need to think about in using genomic tools, or for that matter, any tool that we use in our program, we need to think in the long term, sort of the if I may, the turtle and the hare. If we just race along at the speed of a hare and don't worry about maintaining genetic diversity, there's a risk that we can lose it. But if we're pragmatic, if I could say even wise in the way we design these programs and incorporate genomic information into them, we can make very good rates of gain, yet at the same time safeguard our genetics diversity. We just have to use the tool appropriately.
Okay, very good. And I really liked your sharing the road slide. It hit on all the key points, and one of them is, of course, is the cost of all this stuff. We have some questions coming in on what it actually costs to do one of these chips, and are there differences in what it costs between different ones that you might do, or just give a rule of thumb or kind of an overview of people what they might be looking at here for costs?
Well, the last time I checked with one of the main provider of this service, it would cost at the moment, and this would include both the DNA purification step as well as running one of these genomic chips, it would cost about $125 to $130 per animal for that Illumina ovine chip. So it's a pretty steep price. And part of the reason that's so expensive at the moment in the United States is sort of, I don't know how many of you recall when DVDs first came out. When you first went to the store and tried to buy a DVD, boy, it cost a fortune. But as it became more mainstream and more people bought into that service, the price of these DVD players fell dramatically. That's the state we are in the moment in using these chips in the United States. There's not a huge demand on them. There's not a constant flow of samples going into being evaluated, and therefore the cost is certainly much higher than we see in some other countries that are using this technology. I have some imagination on how we can do better than that, and it goes back to sharing the road. If we go at it collaboratively, we combine samples, run bigger, send in bigger lots of DNA to be analyzed, I think it puts us in a much better position to negotiate price.
Okay. And while we're on that cost question, and you actually answered this question and the reader thanked me for it, but I'm going to ask it anyway because it's an excellent question and I want you to expand on it if you have some more to say. But it's from a young producer and a situation where you only have 16 Texel U's. What genomic tools or tests would be the most effective and affordable for somebody in that type of position to access? In other words, we got a lot of small producers around the country that would fit this picture. How do they get involved in this stuff?
It's an excellent question, and it's one that is a challenge to sheep producers everywhere. When we have very small flock sizes, it becomes really very hard to make large gain individually within our own operation. And so these genomic tools, based on their cost, are probably not going to be the first choice I would make in order to move my flock forward. I think what would help smaller producers most is by collaborating, by sharing that road with other smaller and larger flocks to try to link themselves together genetically. And this is perhaps a different topic altogether, but there's some ways to come together as a larger cooperative. And then what I could imagine happening is in that larger group of sheep, to then, using some of the 4 approaches that I hinted at, identify which animals I would genotype across that entire pool that would end up helping everybody most. It may not be an animal within their own flock. It may be an animal somewhere else that will actually help them increase the ready gain that they can achieve. If I was trying to apply a tool within my own small flock, my focus would probably be on making sure that there aren't some of these major genes at hand that I need to address within my own sheep flock. I'm not sure I would lean towards using these larger tools in that circumstance.
Okay. And just to follow up to that, one of the listeners sent in a message that Texels are one of the key breeds that we need more NSIP flock participation on. So sharing that information. So I got a rather long question here, and it's a good question, so I'm just going to read it as it is. If we are going to selectively genotype rams with higher density chips, would it be ideal to genotype really good and really bad rams for a given trait? I feel like if you genotype all good animals, then there might be a poor prediction of marker effects across populations.
That is a wonderful question. I tease my beef cattle friends that we're going to benefit from all of the silly things that they have done. And this question, whoever asked that question has hit the nail right on the head. There has been a tendency historically to collect genotypes only on the very best animals. And that creates some biases in the way we create these prediction equations, because they're a small, unique subset. They'd be a subset that probably amongst themselves are a little bit more inbred. They're not going to have as much genetic diversity as a breed in its entirety. And so we do need to be strategic in the animals that we genotype. Now, I think I'd be hard-pressed to argue that we choose the very worst animals and the very best animals, because it may be a hard sell for people to want to fess up $100 in genotype animals they would never use. That said, I think we do need to make sure that we properly genotype across our entire population of sheep in whatever breed that we're using. We need to be careful to make sure that we're not too selective in which lambs we genotype, because we want to represent the entire population in its entirety. So I think there's ways to be strategic, to do a better job in identifying animals that will give us the most information, and I'm pretty darn convinced they're not only going to be the very best ones.
Okay. Excellent. We had a question come in on meat quality, and I was wondering this too, when you were mentioning some of the different genetic measures in the carcass and meat quality. I think it was 5 to 10%, if I remember right, from the study from Australia that you mentioned.
Yes.
So when it comes to this, how are we going to deal with eating quality traits, essentially? How are those measured? The shear force, intermuscular fat, lean meat yield. Since offspring will have to be followed to slaughter and physical measurements taken, would you like to address, in general, I guess, the ability of this genomic science to address that meat quality issue?
Eating meat quality is always going to be a challenging one. That's why it's on that difficult to measure trait list. What we would need to do is to clearly integrate commercial industry with the slaughterhouse industry, likely with research university labs, in order to develop a system by which we would be able to start collecting more systematically eating quality data. And it does require, in many cases, a slaughter of animals. There are some techniques like ultrasonics and computer tomography that allows us to get an indication of some of those attributes that is not so invasive. But we would need to think about how we identify animals that we may need to take through to slaughter and to collect those data. There are indeed places in the world where that's done. I've enjoyed the opportunity to spend a fair bit of time in Norway as an example. And they've developed a system where, as part of their norm, every animal that goes through a slaughter facility they're able to get back a carcass weight, a conformation score, and a fat score as their normal operation. So I think it takes a will to move industry in that direction, to develop tools that would allow us to collect that as a norm. But to get at some of these difficult ones like eating quality, I only imagine that can happen by developing a collaboration of different groups that have the skills to measure that and to be very strategic in which animals we would kill and put through to getting that additional information. It's a hard one.
Okay.
No question about it.
And then we got a question on the NSIP. Use of NSIP performance recording includes only a small percentage of the U.S. sheep population at this point. How much does that participation need to increase to have adequate phenotypic data for validating genomic tools?
Yet another good question. I think it has to increase substantially. When I presented that slide of the size of the resource populations, I was hinting that those resource populations on their own right need to be somewhere between 4,000 and 10,000 animals. And at the moment, within most of our individual breeds, and again, those resource populations are within individual breeds, we don't have that number of lambs coming through in a given year. In some breeds, we're probably 2/3 of the way there. In some breeds, we're way far off getting those kinds of numbers. So I struggle to give an exact number because it's somewhat breed specific, but certainly a doubling or a tripling of participation in NSIP is going to be needed just to get us started.
Very good. And a related question, is there a place or need for commercial producers to share animal performance data with their seed stock suppliers to broaden the sample population?
I think there are opportunities there. Again, it entails developing a system to collect data on commercial animals as well as their seed stock parents, if I may. So there would have to be sort of an agreement, a methodology developed, if I may, in order to develop a system for recording that data. But clearly the feedback that seed stock producers can receive from their commercial clients who are doing recording is invaluable in thinking about whether or not we're moving our industries in the right direction. Genomic tools are only going to be will only be valuable if we have a very clear breeding goal in mind, and to develop and to maintain that breeding goal, that communication between commercial operations and seed stock operations is really very key. And the way to really found or base that communication is by integrating data from commercial operations into what we think about as we evaluate our purebred stock, our seed stock.
Very good. And kind of a general question on sheep genomics. How fast is it advancing, and are universities around the world sharing info?
Interesting question. Yes, I think universities around the world are sharing their intelligence, if I may, their wisdom on these tools. It's part of I would like to say, the philosophy of what global science is all about. So I think the knowledge is being shared. The reality, though, is as we develop specific tools, for example, a specific genome chip that we would collect 50,000 bits on our roadmap on, what becomes important is what feeds into the development of that chip. And that tends to be localized to the group that is preparing that particular technology. So there's a general sharing of the knowledge and the ethos, but when it comes down to the development of technologies, those tend to become a little bit more regionalized. And the question then becomes, is a tool developed for one region of the world relevant or appropriate for another? So I think that the communication happens and continues to happen, but when we move it into practice, I think there's a need for, particularly in the United States, for our engagement into actually developing the tool. Okay. There's a second part to that, Jay, that I might have missed?
No, I think that was main part of it was just university sharing information. It was how fast was it advancing was the first part. So.
Oh, right. Pretty soon, we're going to move away from using even these high-density chips to using full genome sequences. It's what's currently being used in the human sciences. It's becoming more ready, available for use in some of the, for example, dairy operations. So just like moving from, the old, tape that we put in our video recorder to these very fancy, high definition discs, as use increases, as skill and technology increases, we're going to move towards using full genome sequences in an effective way. So the technology is moving very, very quickly. Still, the ethos is not going to be different. We need to link that genomic information back to phenotypes to figure out how we can use it to predict animals that have higher merit.
Okay. Another international question. Will breed data from Australia speed the development of U.S. data if Aussie semen is regularly used in the U.S.?
It certainly can. If we can genetically link ourselves to what's going on in Australia or New Zealand or the United Kingdom, wherever wish we might be sharing, we can benefit from that. What it allows us to move towards is incorporating U.S. data with, in this illustration, Australian data in our genetic evaluation. I made the comment related to the question on the smaller Texel flock. Well, we can create those genetic linkages not only within U.S. Texel flocks, but if there are similar levels of recording elsewhere in the world, if we're sharing the use of sires, we can combine the information from sheep being recorded in Australia or the UK or what have you, in with the information we're collecting in the United States. That all helps us do a better job in our genetic evaluation.
Okay, very good. And we have several questions on your project, but before we get that, I want to get through a handful of questions on specific traits related to disease or health issues. One of them is, can we eventually find markers for fecal egg count to help eliminate the use of dewormers?
I suspect we can. I mean, there is a lot of enthusiasm of trying to identify, and it's not going to be a single gene. It's going to be some network of genes that will help us identify animals that are relatively more or less susceptible to parasitism. And we can then use that in genetic selection programs. It is underway today. There's a huge amount of work in the U.S. as well as internationally, where some of these anthelmintic products are no longer effective, and so the only way to address parasitism is through genetic selection. At the moment, it's being done on our current set of tools like fecal egg counts and some other blood metabolites, but ultimately, I believe we can move towards understanding the underlying genetic mechanisms, thereby find the genes that matter and figure out how in combination they work, and then we can use that information to do a more effective job of moving towards parasite-resistant animals.
Okay, and here's one from a person in a wet, warm area. They say fly strike has been a problem in our hair sheep when their hair is too long. Is there any way we can select for shorter hair in our hair sheep? And are there genetic differences in resistance to fly strike among breeds of hair sheep or within breed?
I fear I'm not going to be able to answer that very specifically because I honestly just don't know how much variability there is in our hair sheep breeds in terms of their ability to resist fly strike. Whether or not we can select for shorter hair, and my imagination is we can, because we certainly can affect the length of staples in our wool breeds, really depends on how much genetic variation there is for that trait. My expectation is that there is genetic variability. How much will it impact how quickly we can make change? So I guess that's how do I put that? A reserved yes, but I think there need to be work to be done to understand how much genetic variability there is, and then to think about how to incorporate that into a breeding program.
Okay, and again, in a warm, wet environment, is it possible to select for goats and sheep with resistance to foot scald and hoof rot?
again, kind of stepping back to that answer a moment ago, I believe there is genetic variability for foot sensitivities. I'll group them together that way in sort of a global way. And in theory, that information can be used in selection programs. One of the challenges is actually the measurement of that. There's been a lot of attempts to come up with standard ways to evaluate whether it's scald or rot, and to come up with a very transparent system to evaluate that trait. That's going to be really important simply to have phenotypic measures that we can use. But I think there is evidence out there is genetic variability. If there is, and we can measure it effectively, and we collect the data that we need, given that it's economically important enough, we can certainly think about building it into breeding programs.
Well, very good. And then, as I mentioned, I got several questions on your project, and I'll just run through them, and you can spend as much time on them as you want. But first question, will you be using clustering algorithms like Ward's clustering to determine relationships between populations?
I will. One of the things that the group that I've enjoyed working with, and I suppose I can take some credit for, is a concept called connectedness, and that effectively is a clustering methodology where we can cluster together islands of individuals that are genetically more related to one another. And by so doing and working, I think they mentioned, I kind of missed, Jay, the name they referred to.
Ward's clustering, I believe.
Ward's clustering.
Yeah.
There's different clustering methodologies, but indeed this technique that I'm talking about allows you to create these clusters based on genetic relationships. And what we may want to do is to do our strategic sampling by identifying animals that are in truly separate clusters, because by so doing, we're going to capture more of the genetic variability that we see in the population. And there's some strategies that are being imposed I know, in dairy and in some plant breeding programs that are building on those ideas, figuring out what the clusters are, and then using that information to figure out who you wish to genotype.
Okay. Next question on the project, why only Suffolk and Rambouillet? That quick answer.
Yes. I'm not sure I have a particularly good answer, except it is a start. We were able to begin with 2 breeds with the view that we develop a strategy that then would have a much broader remit, but I kind of want to test these ideas on a smaller set before I inconvenience too many more breeders and in collecting these data. So the choice of 2 breeds really is just a way to get us started to develop the ethos and hopefully the enthusiasm and some of the tools. I would love to see this used across all of our sheep breeds. Thing though, as a side note, and I hinted at it earlier on, reference populations need to be big. And so we need to be careful about overextending ourselves to every single breed, because I fear we just don't have the resources to do it. So as we expand the effort, we need to think about how we do so effectively by identifying those breeds that have the largest role, if I may, within the U.S. sheep industry.
Okay. And how many farms would you want to work with to get the samples? Would regions, western versus eastern states, for example, make a difference?
Well, my guess is as we move across the United States, just by the default that AI is not used commonly, we're going to have greater levels of separation. Our clusters will be more distinct as we move across the nation. And so my hope is that, I'm able to identify breeders and flocks across the United States willing to participate. But as I had put in one of the slides, what is necessarily going to be key is that they're recording with NSIP. So that's going to be sort of my starting point, and luckily I will have access to the NSIP data, including pedigree and performance, to help identify those flocks that are recording performance yet form these distinct groups. I have every imagination they're going to go from the east to the west coast.
Okay, thank you. And thank you to all our listeners for the great questions. Sorry I didn't get to all of them. I tried my best to sort through and cluster them together. But Ron, I really appreciate your presentation and your patience in addressing all those questions. I think you did a great job, and thank you for doing that. And want to remind our listeners we do have some more webinars coming up. Our next one will be on July 19th, so you can mark your calendars for that. We'll have Dr. Dan Moracle of Iowa State University on, and he'll talk about nutrition and supplementation. And his plan is to build off of the webinar that we had last September with Dr. Bob Van Son of Penn State University. So you might want to review that webinar online if you didn't get a chance to see that before logging into that webinar on July 19th with Dan Moracle. He's going to pick up kind of at the tail end of that webinar and build on that information. That was one of our most popular webinars that we've had. So really looking forward to that presentation. I want to thank ASI and the Let's Grow Committee for providing funding for these programs. And I thank all our listeners for tuning in, and encourage you to visit the ASI website at sheepusa.org and to go into the Let's Grow materials, and where you'll find all of these webinars recordings there for you to access. And I will be sending out a follow-up email to this webinar with links directly to those recordings if you just want to click on those or share those with friends who didn't have a chance to join us tonight. So with that, once again, I thank you, Dr. Ron Lewis, for your presentation tonight, and I really appreciate the information you shared with us, and wish everybody a good evening and a happy summer.
Thank you.